So we want to find the area under the curve by forming rectangles for y equals cosine of x from x equals 0 to x equals pi over 2. Alright, so let me show you a rough sketch of cosine. Cosine starts at a high point, and cross, and low point, cross, back to a high point. That is one complete period. However, we're only looking for x equals 0 to x equals pi over 2. X equals 0 is right here. It's our high point. I guess it's kind of off just a little. This really would be like a high point there. And then the cosine of pi over 2 is 0, and that's right here. So if we formed, and we can do this two ways, but if we formed four rectangles starting with the left endpoint, so starting here, again, it being drawn very precisely has a lot to do with if you can tell whether it's going to be too much, give you an upper sum, or too small and give you a lower sum. But draw my rectangles really aren't showing that they would be above. This one over here you can tell. But since this curve is decreasing from right here to here, every rectangle that's drawn will be just a little bit above that curve. Alright, and so how do we find the area of a rectangle? That's going to be height times width. And our width, since the distance from here to here, from 0 to pi over 2, I guess not quite that far, from here to here, that distance is pi over 2. You say pi over 2 divided by 4, pi over 2 divided by 4, and you get pi over 8. So that's the width of each one of these. The height we get by plugging in the x values. Okay, so this is x equals 0. This is x equals pi over 8. This is, add pi over 8 again, that's going to be 2 pi over 8 or pi over 4. Add pi over 8 again, that's going to be 3 pi over 8. And then 4 pi over 8 or pi over 2. Alright, so for each one of those we say width times height, width times height, width times height. Since the width is constant, what you can do is just say the width times, and now to get the height of each one of these rectangles, if we're starting on the left, we use the first 4 x values and plug those into our function here. So that's going to be f of 0 plus f of pi over 8 plus f of pi over 4 plus f of 3 pi over 8. Now if I don't stop there, and if I went on and went to pi over 2, then I'm adding some extra rectangle that in this case has a area of 0 because the cosine of pi over 2 is 0. But we don't want to, make sure you don't have 5 functions here, because then that will be 5 rectangles you'd be making. Alright, so we know that the cosine of 0 is 1. So pi over 8 times 1 plus, I'm not sure what the cosine of pi over 8 is. Let's see, make sure calculators in radians. Pi divided by 8. Take cosine. I'm going to carry this out to 5 places. That's 0.92388. And then the cosine of pi over 4 is the square root of 2 over 2. Now it's 0.707, but let me carry it out to 5 places. I'll just type it in. Pi divided by 4 cosine 0.70711 plus 3 times pi divided by 8. Alright, and then take cosine of that, 0.38268. So add all of that up and say it times pi over 8, and this should give us your upper sum. Alright, so our upper sum is 1.18347 about. And then that's our upper sum. To find the lower sum, we start here using the right endpoint first. So we let our x be pi over 2, so we'll say f of pi over 2, f of 3 pi over 8, f of pi over 4, and f of pi over 8. We just don't use the last one there. So we get our 4 rectangle heights by using those. So that's upper sum there. And the other we say pi over 8. This is for the lower sum now. F of pi over 2 plus f of 3 pi over 8 plus f of pi over 4 plus f of pi over 8. So each one of those is the height of a rectangle starting from the right endpoint. Alright, well that f of pi over 2, cosine of pi over 2 is 0, so it's kind of like we're just losing a rectangle altogether there. And then plus 0.38268 plus 0.70711 plus 0.92388. Now I just got those from the previous problem. Alright, so hopefully I got those right when I did them the first time. Add those together. Alright, so our lower sum is 0.79077. That'll be our lower sum. I usually don't round and carry to 5 places, but since these are estimates, this is one exception to that rule. Alright, so if I want to evaluate this integral, remember absolute value is going to give us a V-shaped graph. This is something that's not super easy to sketch. I mean, it's not that hard to sketch this because you can find zeros and do all that kind of stuff. Let me see if I can sketch that real quick. You could probably use what you learned about graphs in Calculus 1 and finding zeros and absolute maximum, absolute minimum, all that kind of good stuff, and sketch that out. I'm going to plug it in this calculator real quick just to save a little time. Well, looks like I get to start over. Hard to tell that one. Let me zoom in a little bit. You see, we've got a lot of stuff going on here. Notice that you can't get a negative answer. Of course you can't, because you take the absolute value. Kind of bounces everything up, almost like it just reflects that up. You see a good picture of it right here. And so we're integrating from 0 to 4. So we have to figure out a convenient place to split this up between 0 and 4. Alright, so if this is our function, let's see if it'll factor. Of course it should. Something, I at least see you can bring out an x. Alright, so it will factor. So we know that that will always be greater than or equal to 0. Right? Okay. So when will that be equal to 0? Or that's 0. So 0, 3, and 2, this thing is equal to 0. Other than that, it's for sure going to be greater than 0. Alright, so we have to consider x cubed minus 5x squared plus 6x, and consider the negative of x cubed minus 5x squared plus 6x. The tough part is figuring out how to split this thing up. Now, like I said, if you use calculus on a problem like this and you can figure out intervals on which the function is increasing and decreasing, do you remember all of that? If you were to form test intervals after finding these zeros, then you would have negative infinity to 0, 0 to 2, 2 to 3, and 3 to infinity. And in Calculus 1, we learned that, we can figure out on which intervals the function is increasing and decreasing by using test points, and then after that you can use the first derivative test, and you can figure out where maximum and minimum values are, so you can tell where it's going to be increasing, where it's going to be decreasing. We could also, and of course it's kind of cheating, but we could also look at this graph right here, and you can see from negative infinity until we get to 0, we're decreasing. Then from 0 until we get to 2, let's see, we're increasing from 0. I'm thinking this isn't the scale, so we're increasing from 0 to 2. I wonder if I could scroll down there. Yeah, it may look a little better if I zoom in a little. We're not really concerned about this high point. If we were, we could take derivatives and all that, but and figure out where the slope is equal to 0. That's critical numbers. We don't need maximum and minimums, really. All we need is, these are places where the function is equal to 0. And there's another one over here. This far one over here is going to be 3. So we need to figure out the area under this part of the curve. Everybody look up here. We need to figure out the area under this part of the curve. And then we need to figure out the area under this part of the curve. Okay? So I need to zoom out again. This isn't very convenient. But since I'm integrating from 0 to 4, it's going to be kind of hard to see. I need 0 to 2. I need 2 to 3. But it also asks, it doesn't ask, if I just do those two, then that's all I'm going to have is this and this. And that basically is the integral. Let's go back. That is the integral from 0 to 3. But this is 0 to 4, not 0 to 3. So let's look back at the graph one more time. So what I need also, you see there's 3. Look closely. There's 3. There's 4. So if I drew a vertical line here up to where it touches the graph at x equals 4, I want all that area under the curve as well. So I'm going to have to do one integral and integrate from 0 to 2. Then I'm going to have to do an integral from 2 to 3. Then I'm going to have to do an integral from 3 to 4. Okay? I'm going to move this over a little bit. This is a very important concept, and this is probably even harder than the ones you'd have to do on the homework, because you have to split this up into 3 pieces. I'm going to try to zoom around right there. Now, what does a cubic look like if we were just to graph it and not the absolute value? It's kind of N-shaped, right? It would look something like, and I mean this is just the basic cubic. It may look something like this. It may look something like this. It's kind of N-shaped. And if we were to look at our graph right here, this graph comes up, well, it comes down, it bounces up, and it goes back up. So, here it is right here. This part over here, this line, this is bounced up. It would be down here. So I'm going to snip that out and tell you why this is important. Alright, and let me see if I can do this. I'll do this in red. This isn't exact, but this would be down here. This right here would be down here, and then it would go back up. So it'd be kind of N-shaped like that. The parts that are bounced up, that's the negative of the equation. The parts that are in the position that they should be of the graph, those are the positive parts of the equation. I believe the ones on the homework, you don't have 3 different pieces, you'll only have 2. So the part of the equation that looks like it's supposed to, that's the regular function. The part that is bounced up, that's the opposite of the function. So, and that's a little confusing, so I'm gonna show it to you. I'm gonna show you both of the graphs now. So, I'm gonna take, and we know what we need to do, or at least I've told you what we need to do. We need to have an interval for this part. This is going to be the function without the absolute value bars. This part here from 2 to 3, that's bounced up. That would normally be below here. So that's going to be the negative of the equation that's in the absolute value bars. This part here is like it's supposed to be. That's how the graph would look. This isn't changed because of the absolute value bars. This part isn't. So we're just going to integrate it from 3 to 4 of the function without the absolute value bars. Now I want you to see the functions, both functions on the same graph. Let's see if I can just... Okay, so that's good. And let me put in the negative of x cubed. That needs to be squared, doesn't it? Alright. So let's zoom out a little bit. You see, this is the positive of the function, the blue graph here, and the red graph, that's the negative of the function. So you see right here, that piece that's bounced up in our graph of the absolute value is just this positive piece up there. So I told you that if you look at the blue graph, our graph of the absolute value that we had this piece of the graph over on the left side was bounced up. This one right here was up here, was this part. So like if we just took this and then this and this and this, then that is the absolute value. This part, this part, this part, and this part is absolute value. Okay? Now, if we want to integrate from 0 to 4, we're worried about the graphs between 0 and 4. So look at the piece of the graph between 0 and 2. That's this. That's the positive of the function. So that's the first part we're integrating from 0 to 2. Then look at this part of our graph. That's the negative of the function. And then we have to do from 3 to 4. Well, that's back to the positive of the function. Alright, so that can definitely be a little confusing. Why you have to set up 3 integrals, but that is why on this problem you would have to.